Welcome to this video on the acid dissociation constant. We're asking in this video the question, how do you measure the strength of an acid? So acids dissociate in water, and we've seen in the video on Bronsted-Lowry that that's because the water molecules themselves actually get involved and remove a proton from the acid molecule. We've seen that that reaction is reversible. This is going to produce the hydronium ion, H3O+, which is an aqueous state. And it's also going to produce the conjugate base of the acid A-, which is also aqueous. Now, what you've probably come across before when you're talking about acid strength is that this reaction will essentially go to completion for a strong acid, so it will be fully dissociated into H3O+ and A-, so something like this where there's only H3O+ and A- around. Whereas if you have a weak acid, something like this, you've got plenty of HA, the grey molecules here, still present. So the strength refers to the extent of dissociation. In other words, how much H3O+ and A- are present relative to the undissociated acid HA. Now in this video we just want to try and go a little bit deeper in that just as well as you can have weak acids and strong acids, you can also have variability within the weak acids. So here's an even weaker acid. You can see lots more HA molecules here and very few H3O+ and A-. So there's a gradation here between these molecules on the left hand side, very, very weak. On the right hand side, you've got very, very strong. And like many things that you learn about in chemistry, you start up by introducing the sort of extreme cases, strong and weak, and then gradually over time you realize that there's actually a continuum of strength. And mathematics is a powerful tool to help us to understand that. So how do you measure acid strength? Well, here was the equilibrium that we considered in the last slide. The way you're going to do it, you could think perhaps I'm going to use the percentage dissociated, but actually that's not that reliable because that actually varies depending on the initial concentration of undissociated acid you use. So instead we're going to use an equilibrium constant. And the reason for that is because its value does not change with any changes in concentration. It's a constant. It's a constant at least until you change the temperature. And that's really, really powerful, as you'll see when we come to doing pH calculations. And it just allows us with just a single number to be able to summarize how strong an acid is. So let's write the equilibrium constant for this reaction. Kc, they always come in the same form. It's products divided by reactants. So the products we've got here are H3O+. I'm going to drop the aqueous from this. Remember, these are the concentrations at equilibrium with the square brackets. A-, a square bracket just means molar concentration. They're always equilibrium with an equilibrium constant. And we got HA down here on the bottom. So this is the Kc expression, and we should add water in there as well. Now, when we typically write out Ka expressions, we recognise that actually water is present in an incredibly large concentration of about 55.6 moles per decimetre cubed in almost every case. And so we don't really need to include it. Its concentration basically remains constant. So we get rid of H2O. And once we've done that, we can now call this Ka. Ka for acid. Now, the other thing is we often write this in a simplified form. Now, it varies. Sometimes you'll see it with H3O+, but often remember that this is essentially acid in water, and we recognize that we can often just simply write this with H plus instead. Now it just varies, it doesn't really matter as long as you remember when you write it as H plus it's actually H3O plus. So this is Ka. Sometimes you need to be able to work out the units of this. And in order to work that out, you simply take whatever the units would be of the factors that are in the formula and you cancel them down. So this would be moles per decimeter cubed for that concentration, moles per decimeter cubed for this one, and then on the bottom another moles per decimeter cubed. And we can see here that 1 mole per decimeter cubed on the top and the bottom are going to cancel, and that's going to give us overall units of moles per decimeter cubed. So these are the units of Ka. So whenever you see Ka values given for any acid, you will always see the unit moles per decimeter cubed after. Now, final thing is just to summarize, how does Ka actually give us a measure of the acid strength? Well, we can see here that if we go back to the previous slide, we said the strength refers to the extent of dissociation. So if you have lots and lots of H3O plus and A minus around, you're a strong acid. And that will mean this top factor on the top, the numerator of this Ka expression will be large compared to the denominator. So in other words, you're going to have big number divided by small number. That's going to be a large Ka value. So Ka increases with acid strength.